So this matrix from B to Euler that I'm calling the situational awareness matrix, that's a BZism. You won't see it called that anywhere else. But we've spent all this week deriving that, and we saw that it had two problems, right? You had to divide by 0 in there when theta is 90 degrees plus or minus, and we had a lot of trig functions that we had to compute. So if you're computing this at a 45 hertz or higher rate, you have enormous computer load, and you're going to divide by 0 when you go straight up. So yesterday, we derived an alternate way to get situational awareness was through the CBV dot. We derived this. We saw it became a matrix, a skew-symmetric matrix, a rotational matrix, and the elements of this matrix are P, Q, and R, the sensor rate outputs. So we have the sensors located on the axis of I, J, and K. The outputs of those sensors are the elements that go into this matrix. Or, if you wrote, some of you are writing simulations, the output of your simulation, one of the variable outputs is going to be P, Q, and R. That'll be the output of your simulation. So that's what goes in here to compute CBV dot. And once you've got this now, you can compute this at a 200 hertz rate, integrate it to get CBV. And once you've got CBV, you know, you can get theta from this element, take psi and phi. So the arctangent of these two elements gives you the psi angle, and the arctangent of these two will give you phi theta. So you can do this at 200 hertz or faster, no computational problems. And then whenever you want to show the information to the pilot, take the information off this data. Okay? Never divide by 0. It's just that you can't. The third way that we're going to discuss today is quaternions. Now again, I'm presenting you the NASA way to develop quaternions. The quaternion is normally given by a vector like so. It goes from 0 to 3, but the formulas, again, that I handed out, that I received from NASA, go from 0 to 3. And the elements of the quaternion vector are given by the cosine of the rotation matrix over 2. And then these are the 1, 2, and 3, and that's probably why it's labeled 1, 2, and 3. These are the direction cosines of the del Rot vector. Okay, so we'll cover what that is. And the way you work this quaternion system is you convert your Euler angles when you start, and this has to start from an initial condition. You convert from an initial condition into Q, initial condition. Then you get a formula for the rate, Q dot, integrate it like you integrate this. Then whenever you want to show the Euler angles, you go through a conversion back into the Euler angles. Eliminate, divide by 0. There you can see a box. It's the diagonal of a box with the elements I, J, K. And these alpha, beta, gamma are the direction cosines of the del Rot vector. So the angle that this makes with the three primary axes are alpha, beta, and gamma. Okay? So the first angle, of course, is going to be this one between IV and del Rot, and that's going to be alpha. And the second angle, beta, is going to be between del Rot and the J vector. I'm not going to show that one, but I'll show you the third one. So the third one is going to be inside between the K vector, and the gamma will be like so. And beta is going to be between the JV vector and the del Rot vector, and it's not shown. You only really need two angles, for example, if you consider just the alpha angle, just consider the alpha angle by itself, then the red del Rot vector is going to define a cone, a locus which is a cone. All right, and then this gamma vector with the K vector will define 4 lines on the cone that could be possible locus, and the beta vector then will nail down that last line and nail it down. So visually, you only really need 2 visually, and you don't need the last angle. But often you're just given, all 3 of them are given to you. Okay, these quaternions, you take your initial quaternion, which is a function. This is going to be a function of your Euler angles of psi, theta, and phi. that's a vector function, and then you're going to integrate it using the sensor rates, PQR, which come off the vehicle package. And whenever you want to show the output to the pilot, you're going to take whatever Q is every 1/45th of a second or so, and you're going to compute the CBV from that quaternion, and then take the elements as you've done as we did yesterday. Everybody got it? If you don't get what I'm saying, then all these formulas just kind of blend together in a huge haze of notation. But we're always doing the same thing. We want to give the psi theta feed to the pilot, that's the idea, or the ground controller. You want to give them situational awareness. And you can either do it by using that matrix, which divides by 0, or by computing CBV dot, or by using quaternions. Those are the three ways. Okay? All right.